So, we have discussed about the paramagnetism, this classical theory, paramagnetism, so this Langevin classical theory. As well as this quantum theory, and we get the same result. Its chi is equal to c by t, okay. And as I mentioned that in case of quantum theory, what we got this P effective number of Bohr magneton. So, that P effective, it was Gj square root of j plus 1. So, that is the effective number of Bohr magneton. So, then if you multiply mu v, that will be the magnetic moment mu attached with each atoms or ions. So, if you do experiment on this salt, paramagnetic salt of iron group, and the rare earth group, okay. So, this which one is iron group and which one is rare earth group. So, if you see the periodic table, I will show you. If you see the periodic table, so this in this periodic table, so this one is, you cannot see what are the elements. This one is iron group, transition metal. So, here 3D orbitals are having unfilled electrons, and this one is rare earth group, lanthanide group, right. So, this one is having unfilled 4f electron. So, these two groups, this rare earth group, if you take salt of rare earth group and if you take salt of this transition metal group, iron group. So, I think this figure may be, you can see this scandium, then titanium, vanadium, right, then chromium, then this one is manganese, iron, cobalt, nickel, right, then copper, zinc, okay. So, here starting for 3d 1 electron to 3d 10 electron, and here starting from, I think cerium is having F1 electron, and then F1, then F2, F3. So, this is the rvm, Okay. So, these are having the electron in F shell, 4F shell. So, this unfilled shell. So, this unfilled shell, these are 3D electrons and 4F electrons are responsible for dipole moment, okay, magnetic dipole moment, permanent dipole moment. So, if you take salt and measure, do the experiment and measure, find out this P effective value. So, what is observed? So, this one is effective Bohr magnetron number for iron group ions. So, here you see these are the just ion in terms of ion it is written. So, all are having 3d1, 3d2, 3d3, 3d4 these electrons up to 3d9 in copper 2 plus, and these are the spectroscopic term at ground state. What is the spectroscopic term that is written here, and for this P effective, if you calculate, if you know the LSJ value, then we can calculate P effective. So, these are the value. So, if you consider J the total angular quantum number, so then if you calculate P effective, so this is the number, and if you consider only spin angular moment, if you neglect the orbital angular momentum, then you are getting P effective is this one. Now, you see this experimentally this value is found this. So, here you can see the experimental value are close to this P effective, that is 2 s plus 1 to the power half. So, with this P effective value are close. So, so here you can see this is 3.55, it is 1.73, but external 1.9. This is in case of nickel ion 5.59, this is 2.83 and this 3.2. Okay. So, it is close to this when only this spin angular momentum is considered, L is 0. So, in that case this P effective value are close to this. Okay. So, from here, so just I will calculate one and show you. Let me take I think I can take for you this just one example. If I take iron 2 plus or 3 plus, this iron in this case. Okay, let us take iron 2 plus, in this case J value. Now, I think it will be interesting if I take iron 3 plus. If I take iron 3 plus, so in case of iron 3 plus, this electronic configuration is 3d5. So, if I consider just iron 3 plus and this manganese 2 plus. So, both are having the same number of d shell electrons. So, this 3 d5 and 4s2, that's the this s2 has gone for this ionized it. Okay. So, this will not be there, and so actually for iron this is d6 4s2. So, the s2 electron and this 1 electron from d, it is, so that is 3 plus. Okay. So, effectively this 3 D5, manganese 3D5 4S2. So, these 2 plus, so these S2 electrons as ionized. Okay. So, in this case what is basic spectroscopic term? It is basic spectroscopic term, it is 6 S 5 by 2, 6 S 5 by 2. So, I will tell you the meaning, and then P calculated value is 5.92, and in this case also it is 5.92. Okay, so then it will not be interesting in both cases, it is same because L will be 0 in this case. So, then let me take this iron 2 plus, let me take iron 2 plus, okay. So, in this case 3d6 electron, so only 4 S2 electron is ionized. So, then basic this 5d4, this will be 5d4, spectroscopic term will be 5d4, right, 5d4, and this value we are getting 6.7 calculated value using this formula, we are getting 6.70, and if we consider this S P effective, I think I will write P effective equal to Gj square root of j plus 1. Okay. So, this value I am getting 6.70, and P effective, if I calculate Gs, that is basically 2 Gs2 square root of S plus 1. Okay. So, this value is coming 4.90. Okay. And experimentally is found that it is 5.4. Experimentally P effective experiment, that is 5.4, yes, 5.4, right. So, this is the data. So, this from Kittel book, that I am showing from Kittel book. So, I will calculate one. So, you should calculate the others and check it. And then in case of rare earth salt, you can see, in case of rare earth salt, you can see this this P calculated, that is Gj square root of j plus 1. So, whatever value we have calculated value is there. So, experimentally whatever value we got, you can see all are matching well, So, like say gadolinium, so this one, so it is calculated 7.94 and this experimental 8.0. Okay. So, good agreement. And erbium year 3 plus erbium. So, here you can see this calculated value 9.59 and experimental value 9.5. So, I will calculate this one, erbium erbium 3 plus ion. So, its electronic configuration is 4f11, 11 and 5s to 5p6. Okay. And then its spectroscopic term, this spectroscopic term is 4i 15 by 2, 4i 15 by 2, 4i 15 by 2. Okay. And this calculated value 9.59, this 9.59, 9.59 and this is 9.5. So, this is not calculated because all value are well matching with this one gj square root of j plus 1. Okay. So, now question is that why there is a difference in calculated value and P effective experimental value of P effective in case of iron group ions, whereas for rare earth ion the matching with this is quite good. So, this the reason. What is the reason behind it? So, that we want to find out. Okay. So, basically in this case iron group this L is not contributing, only S is contributing. In this case J equal to S, J equal to S, L equal to looks 0, L is not contributing, but in rare earth case it is L is contributing, orbital motion is contributing to the magnetic moment. Okay. So, what is the reason? So, that we want to find out. So, that is called the whatever the reason that is called quenching, orbital quenching. It is called orbital quenching. Orbital quenching. Okay. Orbital quenching, orbital is not responding to the magnetic field as if it is inactive. Okay. So, it is not rotating, it is as if it is fixed, it is inactive, it is not rotating with magnetic field. When we are applying magnetic field, orbital angular momentum is not following the magnetic field, it is inactive, it is fixed. Okay. So, it is not responding to the magnetic field. So, that is called orbital quenching. Okay. So, this orbital quenching is responsible for this difference rare earth and iron group. So, we will discuss later on why in this case orbital quenching is happening in iron group, whereas this in rare earth group it is the orbital quenching is not happening. So, that we will discuss later, but let me should I calculate this. So, this how this 3d6 4s2 for iron atom. So, that you can hopefully can write the electronic configuration, and from there you can get this one. In case of erbium ion also you can find out this electric configuration. Now, atom have this electronic configuration. In case of say iron, I have, so in case of iron 2 plus ion, because 4s2 this 2 electron has gone. So, that is 4s2. So, it is closed subshell. So, its L, S, J is 0. So, we do not bother. So, whatever here unfilled one 3d6 electron. So, it has, so if you find out this total L and this total S for this. So, you will have few number of L are possible, few number of S are possible, and then few number of J will be possible, corresponding J will be possible. So, these are the different possible states of this ions or atoms, right. It can stay in different states having different energy, because J value are different, energy will be different, right. Now, so out of these different states, which one is ground state? Which one is ground state? For any in periodic table, whatever the atoms electronic configuration you are seeing. So, for each atom, if you calculate this LS J value, so you will have a set of number of these values, and that means there are different states, different energy levels, and that atom can stay in any of them. But which one is the lowest energy state, that is called ground state. Okay. So, that we have to find out. So, that is the spectroscopic term, this one. So, this represents the ground state of the that atom, ground state of that atom, right. How to get that ground state of the atom? So, that Hund's rule tells that this, let us do it, and so this d6 electron, d means L equal to 2, L equal to 2. So, it has ml equal to +2 +1 0 -1 -2, right. And then corresponding S, here S, what will be the S value? What will be the S value? So, that one has to find out. So, now Hund's rule is telling, Hund's rule this first rule is telling that you arrange. So, it has, so how many, so here for L equal to 2 I have 5 ml value, means 5 states, right, 5 states. So, you know this called d xy, dy z, d zx, d z square, d x square, minus y square, probably that. So, these are 5 subcells, although they are degenerate. So, now electron, the spin you put for, so I have 6 electron. So, you put this electron in such a way that its spin will be maximum. Okay. So, how to maximize the spin? See, if I put all spin off, that I can put, because without violating the Pauli exclusion principle. So, that I have put 5, and then one more I have to put, where I have to put, anywhere I can put. Okay. So, let us say here I will put. Okay. So, where to put this one? Then the second law tells. So, this first law is maximize S, you put in such a way this S will be maximum, and then second law is telling this, then after keeping this x maximum, so keep S maximum, I can put this one here, right, anywhere I can put, but second law is restricting that one. So, this ml value for this case, say +2, this is +1, this is 0, this is -1, this -2, right. So, this one where to put? So, it is telling second law, then you should maximize L, Okay. So, if I put here then I can put what is the L value for this combination. So, that is the summation of ML basically. So, before putting this summation of this one is 0, right, 0. Now, this one if I put here, so ML will be 0. If I put here, ML will be 2 plus 2, right. So, then this will be the maximum, this will be the maximum if I put it here, if I put it here. Okay. So, this ML, to get the ML equal to 2, okay. So, L has to be 2, L has to be 2. So, in this case maximum S 1 2 3 4. So, 4 into half, so it will be 2, L in this case it will be 2, it will be 2. So, summation of ML is 2. So, to get, if L is not 2, so ML value 2 you will not get. Okay. So, this, and third one is telling that if it is, if less than half filled, then J will be L minus S. If it is greater than half filled, say L will be J will be L plus S, right. So, less than half filled, okay, and greater than half filled, okay. So, it is greater than half filled because half will be 5, so it is 6. So, J will be L plus S. So, J will be, it is telling J will be L plus S, means 2 plus 2 equal to 4. So, L equal to 2, S equal to 2 and J equal to 4, that is the L S J value is corresponding, it corresponds to the ground state of this atom, right. So, so this is the spectroscopic term, how it is written. So, 2S plus 1 multiplicity, it is called multiplicity, then this L value L and then J value. Okay. So, that means here so from here our L equal to 2, L equal to 2 means D, right. So, D we write generally capital D, okay, and our J value is 4. So, J value is 4, and then S value 2, 2 means 5, right, 2 into 2 plus 1, so it will be 5, okay. So, whatever given in the book, that is I have taken from Kittel book, okay. So, from there you can see. So, this exactly I got the same one. So, using Hund's rule one can get this ground state of the atom or of the ion, okay. So, now if you know the spectroscopic term, find out the spectrum for ground state. So, from there itself you will get LSJ, or opposite if you calculate LSJ for ground state, and then you can find a spectroscopic term, okay. So, now if you, so if what is this, you see this P effective for J is GJ, one has to calculate what is GJ. So, the 1 plus J plus 1, right, plus S plus 1 etc. You know these two J plus 1, right, J plus 1. So, you calculate it, okay. If you calculate, you will see this, you will, I will not calculate, it will take time. So, but just you calculate and check it, and then just taking S equal to 2, here J equal to take 4, calculate this, and then you will exactly will get this value, Okay. And for this erbium, this one just the way I have done the same way you should do this one. So, this F11 means it will follow this J equal to L plus S. Okay. And so, for F means it will be 7, 14 electrons it can take. So, it will be 7. So, you put 7. So, ml will be 0 and then you have additional 4. So, out of 4, so that unpaired electron spin of electron 3 will be there. So, 3 means half plus half plus half 3 by 2. So, S will be 3 by 2, S will be 3 by 2, then 2s plus 1, 2s plus 1, right, multiplicity 2 into S half, S 3 by 2 plus 1. So, this 3 plus 1 4. So, exactly it is 4. Okay. So, you just calculate, check it, practice for other I have shown you list. So, for all you calculate this, and another one is this one for iron group. So, just whatever this result is given, just check it and it will be good practice for you. So, yeah. So, I think this is the so from this what we conclude that iron group, salt of iron group, it is paramagnetic, but from there whatever this P effective value we are getting, so that is telling that L is quenched, L is not contributing. In case of rare earth, it is not L is contributing with S, and thus the J is the effective angular momentum, and corresponding P effective value we are getting, which agree with the experimental result. So, now what is the reason behind it, why this orbital is quenched? Okay. So, if you see the for iron group, so electronic configuration is 3D. So, I think in here you have what is the combination there? I think argon 18, I think argon, that one is argon, then 3D 4s2, 3D 4s2, right. And for rare earth, I think I should write iron group, and for rare earth what we got? I think this is xenon, yes, and then you are getting 4f. I am writing x number of electrons, and then 5s2, 5p6. Okay. So, if you look at these two, so this 3D as if this is the outermost shell, whereas these 4f are quite inside, because outside these 5p are there, right, 5p6 electrons are there. Okay. So, this shell is protected by this 5p shell, right. So, 5p shell, this electrons are there, and inside this 4f, right. In case of iron group, 3D are outermost shell, okay. So, if now whatever we have done to for paramagnetic, for diamagnetic, just we have taken isolated atom, because we have not considered that there will not be interaction among the ions, right, among the dipole moment of the ions or atoms, right. So, that means it looks isolated, it is paramagnetic gas kind of things, right. But that was the I think that was not the realistic assumption, because these atoms, iron or rare earth, whatever this solid we are taking. So, these ions or atoms are in a solid, right, are in a solid. Okay. So, if I consider this one, this say iron ions or rare earth ions or whatever. So, here this there will be influence of this other, presence of this other neighbors, other neighbors. Okay. So, it is basically the electronic structure of this, if they are same also, there is no problem. So, there will be, it will generate, these neighbors will generate some, that is electric field when atoms are in a crystal. Okay. So, neighbors of this one will generate some electric field. Okay. And that this, so this is under electric field. Okay. So, there will be effect of this electric field on these ions, right, on this end. So, it is not free, it is not free. So, means it has no effect with there is no effect on this from the neighbors. It is not the case, there is effect. Okay. So, that is called crystal field, that is called crystal field. Okay. That is called crystal field. Now, due to this crystal field, why this crystal, from where it is coming, this, and it is electrostatic nature, electrostatic nature. So, this, due to this crystal field, this type of some influence from the neighbor on this, so this its electronic structure affected, these shells are affected, right, which are contributing to magnetic moment. So, they are affected. So, now in this case, since it is outside, it is outside, right. So, this effect, this will be affected more, this shell will be affected more than this, because this F shell is contributing to the magnetic moment, F shell, but F shell is there, and outside that P shell is there, P shell is there. So, from this field, it is in some extent it is protected. So, it is not reaching to this 4F shell in F shell, okay, and not getting disturbed, right. So, that's the reason why in this case, that whatever calculation we have done considering the isolated ions. So, as if this rare earth one, this looks isolated, because it is not having any effect from the surrounding, whereas this iron group is having the effect from the surrounding. So, due to this crystal field, it is affecting the D shell. So, what happens? Two things may happen. One is LS coupling will break. Right. And second is this energy levels 5 ml, right. If L equal to 2, 5 ml, this energy level, they are degenerate, and due to this crystal field, this degeneracy is removed. Okay. So, generally it tells this here 5 are there in case of D shell. So, it is written T2G and EG in these two groups. So, T2G and EG, how it is defined? So, this distribution of this angular distribution of the charge, angular distribution of the electronic charge in the shell, D shell. Okay. So, as I told that dxx, dxy, dyz, dz square. So, this indicates the, so I will show you I will show you. You see, this in case of S shell, this is the spherical symmetry of the charge. So, I have done. So, here it will take time to draw. So, that is why. So, this S shell, and for Px, Py, Pz, Px along the this lobes along the x direction, this one along the y direction, this one along the z direction, right. Similarly, in case of D there are 5, in case of D there are 5, yes there are 5. So, this is dz square. So, it is along the z axis, and this is dx square minus y square. So, this is it is along the x axis and along the y axis, these lobes are along this direction. dxy means it is between x and y axis. So, it is not along the x axis or y axis, but it is in this plane and it is along the between these two axes. Okay. So, in this case also same, this dx z, dy z. So, this the T2j, that is defined that where these electrons, that charge distribution, angular distribution is not pointed towards the axis. Okay. And other one is Eg, where these electrons are charge distribution, angular distribution is pointed towards the axis. Okay. So, that is why it is Eg. Okay. So, two groups are there. So, so without applying magnetic field, if we apply magnetic field, they are splitted, that we know, Zeeman splitting, right. Without applying magnetic field, due to crystal field, these two are separated, these two types are separated. Okay. So, here I think it is the which one is higher, that I have to see. Okay. So, that is T2g is higher and no, Eg is higher. So, this will be Eg, okay, and then that will be T2g. So, this nomenclature. Okay. Now, again what happens, this sometimes what happen. So, they take two types of bonding, this tetrahedral and octahedral. Generally, most of the case it takes octahedral. So, which one is octahedral, which one is tetrahedral, that I can probably I can tell you. Okay. So, I have drawn here. So, this the octahedral, So, means this ions D shell, that ions, say iron ions is here, and then it is surrounded by say oxygen. So, they say Fe2O3 or Fe3O4. Okay. So, this type of in that case. So, tetrahedral and octahedral, two kinds of there. So, here it is called octahedral because it has, you can see 8 facet. Okay. And tetrahedral, it looks like this. I have drawn here, it looks like this tetrahedral, as if you can consider this cubic cell. So, in middle that your ion, and this surrounding, this may be oxygen or some other attached with this one, some forming bonding. So, this is the octahedral. So, this if I draw, it is say this one. Okay. So, these three, I think yeah. So, this is in middle and these three are the say oxygen. So, in this case it will have 4 facet. Okay. It will have 4 facet. So, tetra means 4, octa means 8. So, that is why it is called tetrahedral. So, so in which environment your ions is there. So, whether it is in tetrahedral or it is octahedral. So, that is the effect of surrounding on the ion. So, that changes the sometimes affects the orbitals which is associated with the magnetic moment, Okay. So, so this is the reason of crystal field, and due to crystal field there is a splitting, there is a degeneracy is removed, and this one what happens sometimes, this whatever tetrahedral I showed you, right. So, this tetrahedral sometimes it is distorted, you know, automatically distorted. When it is distorted, its elastic energy increased, but its electronic energy decreased, so that this total energy of the system will be lower. So, to minimize the energy of the system, sometimes it happens that system distorted itself, and because of that, because of this distortion, then again this degeneracy again further it may remove, and it happens that this in this case this degeneracy is removed, and in this case also the degeneracy is removed. Okay. Here one and here this. So, only these two are degenerate. So, they are separated. So, which one? So, this one I think d I have written dx square minus y square, this one, and dz square. Okay. So, whatever things is important here, just I want to say that this in crystal, this ions which is contributing to the magnetic moment. So, that is affected by the environment, by the neighbors, so by the crystal. Okay. So, it is different, situation is different than the isolated ions. So, because of so whatever moment we have calculated by whatever calculated consider the isolated ion. So, result is different because of this crystal field, and that is the reason of quenching, orbital quenching. So, I will stop here. Thank you.